Imagine if you could break free from Earth's gravitational pull, soaring high above the stars to look down upon our celestial neighborhood. You would see our home, the Milky Way, resembling a glowing pinwheel spinning silently in the vastness of space. It appears serene from a distance, yet this stillness masks a relentless cosmic engine. Within its bounds, stars undergo an eternal cycle of birth and death, entire stellar systems hurtle at unimaginable speeds, and colossal clouds of gas drift, explore, and ignite. Deep within the heart of the galaxy lies a sleeping titan. Only recently have we begun to truly comprehend the Milky Way's true form. We have mapped its spiral arms and discovered its satellite galaxies, yet so much remains shrouded in mystery. In this journey, we will follow the evidence to piece together one of the most magnificent stories in the universe, the biography of our galactic home. This is a long tale. So let us begin the narrative, but before we dive deep, please remember to like, share, and subscribe. If you were to visualize the Milky Way from the side, you might imagine it as a perfectly flat spiral disk, much like a giant cosmic vinyl record. For many years, this was the prevailing scientific view. However, as we peered closer using radio maps, space telescopes, and stellar surveys, this simple image began to fracture. We discovered that the Milky Way bulges and its edges ripple like waves on a windswept pond. These irregular shapes reveal a deeper history of the galaxy's birth, evolution, and ultimate destiny. The most prominent feature is the central galactic bulge. From our vantage point within the spiral arms, our view of the center is obscured by thick veils of cosmic dust in the visible spectrum. But by utilizing infrared and radio waves, scientists can penetrate this shroud to see what lies behind the fog. The results show that the center is not a perfect sphere but is stretched into a bar-like structure that serves as the backbone of the inner galaxy. This barred bulge is common in spiral galaxies and is thought to be the result of the internal rotation of the disk. Over time, stars and gas congregate and stretch under the influence of gravity. This structure drives gas inward, fueling the birth of new stars and potentially feeding the central supermassive black hole, acting as the engine for the core's activity. Surrounding this bar is a population of ancient, red stars, relics from the galaxy's early life. Yet, even among these elders, pockets of gas remain where new stars continue to ignite, marking a convergence of the ancient past and the far future. Moving away from the center, the galactic disk exhibits strange distortions. It warps. The outer disk of the Milky Way resembles a record warped by intense heat, with one side curving upward and the other downward. This warp dictates the distribution and motion of stars and gas. Astronomers have used radio observations of hydrogen gas to map this deformation with precision, finding similar ripples in the distribution of stars. This curvature is asymmetrical. Some regions exhibit a more pronounced twist, while others flare outward like the crest of a breaking wave. The cause of this deformation likely stems from external disturbances. Our galaxy does not exist in isolation. It is surrounded by smaller satellite galaxies that have collided with or brushed past us throughout history. These interactions tug at the edges of the disk like someone pulling on the corner of a tablecloth, leaving waves and twists in their wake. A prime suspect is the Large Magellanic Cloud, whose massive gravity may be causing the disk to oscillate as it passes by. Another possibility involves the uneven distribution of dark matter. If the dark matter halo surrounding our galaxy is asymmetrical, it would exert varying gravitational forces, causing the disk to tilt and warp. Further out, the disk flares, meaning it becomes thicker toward the edges. These outer stars and gas clouds do not stay strictly within a flat plane but rise into a bowl-like shape, a sign that the outer reaches are more vulnerable to the gravitational influence of passing galaxies or dark matter clumps. The vertical structure of the Milky Way is far from rigid. Not all stars follow a flat, orderly path, some bob up and down in their orbits, creating wave-like motions. These fluctuations may be the scars of past galactic mergers. When a smaller galaxy is consumed, it sends ripples through the Milky Way like a stone cast into a still lake, ripples that remain visible in stellar motions billions of years later. Europe's Gaia satellite has confirmed these patterns by measuring the trajectories of over a billion stars. Every twist, bulge, and flare is a record of the galaxy's interaction with its environment. These features tell us that the Milky Way likely began as a collection of gas and stars that grew through gravitational accretion and mergers. The scars we see today are the living history of that long, transformative journey. If viewed from the right angle, the center of the Milky Way reveals a peculiar shape resembling the letter X. As infrared telescopes pierced the dust clouds, they revealed a sea of stars pulled into the barred structure. However, this bar is not smooth, it has thickness and distinct layers. Data from space telescopes show that when looking slightly above or below the galactic plane, the central bulge displays four bright, arm-like structures. Unlike the orderly orbits in the spiral arms, the stars in the bulge follow complex, elongated paths. Some are lifted high above the disk, creating a boxy or peanut shell profile. This boxy bulge is a result of a process called bar buckling, where a once flat bar becomes unstable under its own gravity and bows outward. This suggests that our galaxy's core grew from the inside out, rather than through external collisions alone. Most stars here are red giants over 10 billion years old, and by studying their movements, scientists can reconstruct the shape of the core even when they cannot see it directly. Some researchers suggest the existence of a smaller inner bar nested within the primary one. If true, this double bar system would further stir the motion of gas, accelerating its flow toward the central supermassive black hole known as Sagittarius A star. While this black hole is relatively quiet today, evidence suggests it was far more active in the past, likely triggered by the gravitational influence of the bulge and bar. Meanwhile, the spiral arms are filled with cold, dense clouds of gas and dust, the nurseries of the galaxy. Here, the youngest and brightest stars are born. These hot, blue stars have short lives but serve as lighthouses marking the positions of the arms. We currently recognize at least four major spiral arms: the Norma, Scutum Centaurus, Sagittarius, and Perseus arms. Our solar system resides in a smaller branch called the Orion spur. The spiral arms are not fixed structures of permanent matter, they are more like cosmic traffic jams. Stars and gas move in and out of these regions of high density. As gas clouds enter an arm, they are compressed by gravity until they collapse to form new stars. This is why the arms shine so brightly. They are illuminated by the blue-white glow of newborn stars. These massive stars live fast and die young, eventually exploding as supernovae. These explosions send shock waves through the arms, clearing out cavities and influencing the next generation of star formation. These regions are rich not only in hydrogen but in complex molecules like carbon monoxide, which scientists use to map these nurseries. Famous regions like the Carina Nebula and Orion Nebula provide us with close-up samples of this process. While the exact number and shape of the arms are still debated due to our limited perspective from within, missions like Gaia are helping us resolve these mysteries with unprecedented precision. The spiral arms are not eternal, they shift, fade, and evolve over eons. But in this current moment, the Milky Way is in a vibrant phase of its life, surging with energy and new creation. Near the very center, the stellar density reaches its peak. Here, we find massive, compact star clusters like the Arches cluster and the quintuplet cluster. These clusters contain some of the most massive and unstable stars known, living in an environment where stars are packed thousands of times more densely than in our neighborhood. At the very heart lies the nuclear star cluster, surrounding the central black hole. In this extreme environment, stars are so close together that they frequently interact gravitationally, sometimes being flung out to the galactic fringes or captured by the black hole's gravity. Observing these regions is a challenge, but through infrared and radio windows, we can track the motion of stars in this intense gravitational field, allowing us to weigh the central black hole and understand its profound influence on the galaxy's evolution. These dense clusters act like the celestial dancers of the galactic treasure, interacting with the central black hole to maintain the dynamic equilibrium of the core region. Their presence not only sculpts the landscape of the galactic center but likely leaves a profound imprint on the long-term evolution of the Milky Way itself. Deep within the innermost sanctuary of our galaxy resides an invisible yet incredibly powerful entity known as Sagittarius A star. This is a supermassive black hole with a mass roughly 4 million times that of our Sun, yet it is compressed into a region smaller than our own solar system. Although the black hole itself cannot be observed directly, its gravitational influence on surrounding stars reveals its presence beyond any doubt. Over the past few decades, astronomers have used high-precision infrared observations to track the trajectories of stars orbiting this dark heart. The most famous of these is S2, which completes an orbit every 16 years. At its closest approach, S2 reaches speeds of 7,600 km per second, fast enough to circle the Earth in just a few seconds. Such extreme motion can only be explained by the crushing gravity of a supermassive black hole. While Sagittarius A* remains relatively quiet most of the time, it is not completely dormant. Occasionally, gas and dust falling into its gravitational grip form an accretion disk, releasing high-energy radiation and flares before being consumed. Astronomers have observed these brief bursts of brightness in X-ray, infrared, and radio bands. These flares are like the heartbeat of the black hole, reminding us that it remains an active force. History suggests it may have been far more violent in the past. Observations from the Fermi Gamma Ray Space Telescope revealed two massive bubble-like structures erupting from the galactic center. These Fermi bubbles extend 25,000 light-years above and below the galactic plane. They are likely the remnants of a period of intense activity millions of years ago when Sagittarius A* devoured a vast amount of matter and ejected high-energy particles. Today, we possess more advanced tools than ever to study this core. In 2022, the Event Horizon Telescope captured the first image of the ring-like structure surrounding Sagittarius A star. Although the image was affected by the black hole's rapid rotation and variability, it provided our first direct view of the threshold of the event horizon. Studying this titan is not just about understanding the nature of black holes, it is a key chapter in the story of galactic evolution. Supermassive black holes and their host galaxies share a symbiotic relationship, where their masses and growth rates appear linked in a long-term co-evolution. The history and future of the Milky Way are inseparable from this silent, powerful heart. The galactic center is more than just a stage for stars and black holes, it is filled with vast amounts of gas, powerful magnetic fields, and ongoing high-energy physical processes. Because most of these phenomena are hidden behind dust, we rely on multi-wavelength observations to reveal their true nature. First, there is the gas structure. The distribution of gas in the core is extremely complex, ranging from ionized gas at millions of degrees to molecular clouds near absolute zero. These molecular clouds are the cradles of stars, surviving the intense gravity and radiation to form structures like the central molecular zone. This zone spans hundreds of light-years and contains some of the densest gas clumps in the galaxy, serving as the potential source for future star formation. Beyond the gas, there is a powerful magnetic field. Radio observations have discovered numerous long, thin magnetic filaments, some stretching for dozens of light-years while remaining remarkably straight. These filaments are likely the result of magnetic fields being stretched on a large scale, interacting with high-energy electrons to emit synchrotron radiation. These fields influence the movement of gas and may play a vital role in regulating star formation and guiding the flow of high-energy particles. High-energy phenomena are common here. In addition to the occasional flares from the central black hole, the core region possesses a steady background of high-energy radiation. This radiation originates from supernova remnants, intense stellar winds from massive stars, and the acceleration of electrons and protons within magnetic fields. These particles produce gamma rays, X-rays, and radio waves, making the core exceptionally bright across the spectrum. The dynamic processes of the core act like a giant engine, constantly transforming energy between different forms. Gas is compressed into stars, stars release radiation and particle flows, and this matter is either swallowed by the black hole or ejected further into the galaxy. This cycle maintains the vitality of the galactic center and influences the gas supply and star formation rates for the entire Milky Way. By researching these hidden activities, we can compare our core with those of other galaxies, revealing universal laws of how black holes and galaxies evolve. Together, every flare and every gas jet is a signal sent from this massive system to the outside world. Observing the galactic center is far from simple. We are separated from the core by 26,000 light-years of dust and gas that absorb and scatter visible light, making the center invisible to traditional telescopes. To peel back this natural veil, astronomers must rely on wavelengths that can penetrate the dust, such as radio, infrared, and high-energy X-rays and gamma rays. Radio telescope arrays like the Very Large Array and ALMA can map the gas structures and magnetic fields. Infrared telescopes, such as the Very Large Telescope in Chile and the Keck Observatory, track the precise motions of stars to confirm the black hole's mass. The challenges do not end there. The stellar density in the core is so high that thousands of stars overlap in our field of view. To distinguish them, astronomers use adaptive optics. In the high-energy spectrum, space telescopes like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope detect flares and particle jets, capturing the fleeting details of black hole activity. The Event Horizon Telescope recently connected radio dishes across the globe to create an Earth-sized array, achieving the resolution necessary to photograph the shadow of Sagittarius A star. This was not just a technical victory but the first time humanity truly saw the silhouette of our galaxy's heart. These technical breakthroughs bring us closer to the truth while revealing new questions. We can observe many phenomena in the core but cannot yet fully explain the causal links between them. Future instruments like the James Webb Space Telescope and the Square Kilometre Array will continue to push our boundaries. The core is like the central square of a bustling city, teeming with energy, and we are slowly learning how to see every detail in this crowded space. The galactic center is a key to understanding universal patterns. Nearly every large galaxy hides a supermassive black hole at its center, and the interaction between these holes and their surroundings plays a crucial role in the evolution of the universe. Through Sagittarius A*, we have a local laboratory to observe how a black hole's activity is fueled by its environment and how its radiation regulates star formation. These processes were likely more violent in the early universe, but here we can study them with high resolution. The galactic center is also a hub of extreme physical conditions, including strong gravity, intense magnetic fields, and dense stellar populations. These conditions mirror many of the universe's most extreme phenomena, providing a reference for studying gamma-ray bursts and particle acceleration. Furthermore, the cycle of star formation and chemical elements in the core is essential for understanding the chemical evolution of the cosmos. Heavy elements forged in supernovae are released back into gas clouds, driving the birth of new stars and planets. This cycle not only shapes the galaxy's structure but provides the material foundation for life itself. Philosophically, the galactic center is a feature we might share with other civilizations. No matter where they are, if they live in a large galaxy, their sky likely contains a bright and powerful core. Perhaps one day, our signals will be reflected or amplified by this core, traveling across cosmic distances. The center of the Milky Way reminds us that Earth and humanity are but a speck of dust in a vast system, which is itself one of billions. To understand the core is, in a sense, to understand the heartbeat of the universe. The exploration of the galactic center is a collective journey for all of humanity, involving science, technology, culture, and philosophy. Every upgrade to our telescopes and every clearer image is a result of global cooperation. In the coming decades, new capabilities from the James Webb Space Telescope and the Square Kilometre Array will reveal even deeper structures. We may even measure the very pulse of the core. In the far future, we might send probes toward the center, navigating through the dense stellar fields to experience that realm of gravity and radiation directly. This would require immense breakthroughs in propulsion and deep space survival, but it would mark the first time humanity truly walks toward the heart of its own galaxy. Exploring the core is also exploring our relationship with the cosmos. It reminds us that our civilization, our Earth, and our Sun are just small eddies in a vast, breathing, and evolving system. Perhaps one day, when humans have spread across the Milky Way, we will look back at today's blurry images of the black hole as if looking at a portrait of an ancestor, with both awe and familiarity. It will be the starting point of a civilization that decided to look up and move forward. That concludes our sharing for today. I hope you have a wonderful dream, and I will see you in the next episode.